In this video, we're going to investigate equilibriums related to solubility. If you'll remember, when we first studied precipitation reactions, we had some outcomes that were labeled slightly soluble. If we were to make these chemicals and put them into a solution, we would see that most of that substance doesn't dissolve, but a little bit of it does. This is known as the solubility product. To some extent, every ionic substance will dissolve. It's just going to be an equilibrium reaction. Every single solubility reaction is going to be an equilibrium reaction. If our equilibrium constant is very heavily favored to the right side of the reaction, which means heavily favored to the ions dissolving in solution, that's when we say something is soluble. But everything will dissolve to some extent, and now that we understand equilibrium, we can actually investigate how those reactions will take place. And to do that, we're going to use a tool called the Rice table. Rice stands for reaction, initial, change, and equilibrium. It's useful to look at first the reaction. And we're using silver chloride here, a fairly simple, slightly soluble reaction. Silver chloride will break up into silver ions, silver cations, and chlorine anions. Our initial concentration is going to be the initial concentration when we start our reaction, which this reaction would start with AgCl being put into a solution. So when it's first put in, we have some mass of AgCl. Now that doesn't matter because this is a solid. But the silver and the chlorine will both be dissolving. But when we first put that in, nothing has happened. So our initial concentrations are 0. And then we're looking at the change. And the way we use a Rice table is we go, well, how are these going to change? And this is where we use our stoichiometry. In both of these cases, we have a 1. This is a 1-to-1 relationship. And so we can say that these are going to change by the same amount. We're going to call that amount x. And then our amount at equilibrium, both of these will be equal to x. If we had something on the left side, if we had something that was going to change, then what we would say is, let's say it started at 3 molar, it would be 3 molar minus x. And we would be able to use that in our expression. However, solubility products are pretty straightforward when we use a Rice table, so we don't need to include any of the reactants. And so then, once we have this set up, since this is going to change, this is going to be plus x. Our KSP, we have a value for. But we can also create an equation for it. Our KSP is going to be equal to the products divided by the reactants, just like in any other equilibrium. And because the AgCl is a solid, it doesn't get included. And so our KSP is simply going to be the concentration of silver times the concentration of chlorine. And because when that gets put into a solution, it's going to change by that plus x amount, and at equilibrium it's going to be equal to x, we can really put x in for each of these. And so I can say KSP equals x times x, or x squared. Now, this is very useful because I have the value of KSP. It is 1.8 e negative 10, and because that equation ends up being x squared, I can take 1.8 e negative 10 equals x squared, and I can figure out the value of x. I can figure out what my final concentration of silver and chlorine is going to be by taking the square root of both sides. So let's do that. And when I do this calculation, I get for x the value of 1.3 e negative 5. And what that means is that my final concentration of silver and chlorine will each be equal, let's just write silver up here, will each be equal to 1.3 e negative 5. Now, when I have these ionic substances, these solubility products that are breaking up at a 1-to-1 ratio, it is as simple as that. I'm going to get x squared. But what about when I don't? Let's set up a rice table for something like copper hydroxide. Copper hydroxide could have a KSP of 3.3 E negative 16. And now I'm going to do the same thing. My initial concentration for CuOH2, we're not going to worry about it because it is a solid. But for Cu2+, it's going to be 0. And for OH-, it's also going to be 0. Now, how much are these going to change? For each mole of CuOH2 that gets broken up, I would get 1 mole of Cu2+ and 2 moles of OH-. That means that the change for Cu2+, is going to be plus X. Notice, this would be a 1 here, so this would be a 1 here. But the hydroxide has a 2 for its stoichiometric ratio, which means it's going to be plus 2X. Okay? Now, at equilibrium, that means that the final concentration of Cu2+ will be X. The final concentration of OH- will be 2X. Fantastic. Now let's see how that relates to our KSP. Our KSP, equilibrium of our solubility reaction, will be the concentration of Cu2+ times the concentration of OH-, but that OH- would be squared. Now, I take this X, I put it in here, I take this 2X, I put it in here. And I get X times 2X squared. 2X squared because of that square right there. So what this really comes out to is 2X cubed. So now when I take my 3.3 E negative 16, this is going to be equal to 2X cubed. Now when I want to solve this reaction, this equation, when I want to solve for X, first thing, divide by 2. We get 1.65 E negative 16 equals X cubed. Now, in order to get X, we need to do a cube root. Now, how do we do a cube root? Some calculators will have this function, this root with an X here, so that you can tell it what degree of root that you want to do. You might have a key that looks like this, that has a 3 there. But eventually, in solubility products, even in solubility products, we might have to do a root that might be a 5 root. And so to do that, if your calculator does not have this simplified option, the easiest way to go about this is to recognize that a root, a square root, is the equivalent of taking x to the 1/2 power. So if I take the square root of x, it is x to the 1/2 power. If I take the cube root of x, it is the same as x to the 1/3 power. So that's what we're going to be doing here. We're going to take x to the 1/3 power. That'll get rid of this 3. And then I take this 1.65 e negative 16 to the 1/3 power. But this is where we need to be very careful when we enter things into our calculators. So I'm going to be entering in 1.65 e negative 16, and then I'm going to take it to the power of, and I'm going to use parentheses, 1/3. What would the calculator think if I did not use this 1/3? If I did not use that 1/3, the calculator would think I meant to do 1.65 e negative 16 to the power of 1 and then divide the whole thing by 3. If I don't use that parentheses the right way, I get a very different answer. And so when I take this number, I should end up with 5.48 e negative 6. Okay? And that is going to be the value of x. Now, we're not quite done. These can be challenging problems. These can be very challenging, but we're not quite done. We now have the value of x, and we saw here my final concentration at equilibrium for copper For the copper 2 plus anion, my equilibrium concentration was X. So the concentration of copper, if I take the concentration of copper, Cu2 plus, that is equal to 5.48 E negative 6. Totally fine. That's going to be molar, by the way. But what about the concentration of OH? Well, the concentration of OH, if I look back up at my rice table, ooh, that's not what I wanted to do. If I look back at my rice table, I had 2 OH and 2X for my final concentration. So I need to take the value that I found down here of X and multiply it by 2. And I end up with 1.0, that's actually going to round to 1.1 E negative 5 molar. There we go. Those are our final concentrations for both of these. Let's try one more that is very complex. So I've got aluminum oxide here breaking up. Remember, this is a solid, so it's not included in our solubility expression. I have an initial concentration of 0. For all of these, it's going to be 0. We're not going to deal with anything too complex where we have anything above 0, but we want to practice doing this rice table because it'll really come in handy, especially in college level chemistry. My change here will be a plus 2x. 2 because of my stoichiometric ratio. And then my change for my oxygen will be plus 3x. 3 for my stoichiometric ratio. My final equilibrium concentration for aluminum will be 2x. Final concentration for oxygen will be 3x. So when we put our KSP equilibrium together, we get aluminum 3 plus squared times O2 minus cubed. And so we're going to take the 2x, we're going to plug it in for the aluminum 3 plus, and the 3x we're going to plug in for oxygen 2 minus. And so we end up with a 1.94 E negative 19 equals 2x squared, a little more room, times 3x cubed. And when we put that together, we get 1.94 E negative 19 equals 6x to the 5th. Now, let's get this all figured out. First thing, I want to get rid of this 6. So I'm going to divide both sides by 6. That leaves me with 3.23 E negative 20 equaling x to the 5th. Now I need to take the 5th root of this. So remember, I'm going to take 3.23 E negative 20, missed my decimal point there, and I'm going to take that to the power of 1 over 5. When I do that, I will get x. So I need to make sure I put that 1 over 5 in parentheses when I enter it into my calculator. And I end up with 1.26 E negative 4 for my value of x. But I'm still not quite done because remember, my final concentration of aluminum is 2x. So if I want to know the concentration of aluminum, I need to take that value times 2, and that's going to be 2.52 E negative 4 molar, more room, molar. And then my concentration of oxygen, O2 minus, let's put my, be a little more accurate there, is going to be 3x. So it's going to be 3 times 1.26 E negative 4. And that'll be 3.78 E negative 4 molar. And that is my final answer. So when I'm looking at these solubility products, what I'm really doing is I'm using this rice table to build a custom equation with a known equilibrium constant that allows me to predict the final concentration of my substances.